It's true. Otter, my best supporter. I'll never forget you, Otter. I'll never forget you. My number one supporter through thick and thin. Don't worry. Poem streams are coming soon. Never forget Otter Nation. I never will. Poem streams never go away. Don't worry. I'll be back one day. Just wait for the time. Wow, this playlist. The comeback's gonna be more than muddy. It's gonna be gruddy. Very very gruddy. Okay. You know, I have a feeling it's... There we go. I had a feeling it wasn't sharing the screen. Okay. Expect the suspicious poem stream sometime in the next 2 weeks. Perchance it might happen. Who knows? You never know when it might happen. You never know. The little those who know moment. That's for those who know. Say hi to you. Hey Winter MLC. How are you doing today? Good old Winter MLC, huh? I hope your name doesn't start with an S or anything. Because that wouldn't be really good. You're not my number one fan. My number one fan is actually some Otter Things. He's been here since the dawn of time. He's my original goat. He is Otter. He is the one who's been here since the beginning. And like this is retro timeline. Here I was born. Right about here in 1967. This is my birth date right here. I was born here, and then Otter comes in right here. Yeah, but this Otter. What year was that? This was what it was like. 19. Well, it was what 19. I think you came in at 1965. Like I think you came in like before I was born, but somehow it's all, like it's in front in the timeline. So I don't know what happened there. But this is Otter. Like this is Otter's appearance. 2 years before I was born. He just spawns out of nowhere. Not sure that happened. And he fast forwarded it out, and now we're in the year 2026. And then this fraud Winter MLC thinks they can compete with Otter. Not possible. That's enough. Enough of that. Yes, impossible like EBW. Okay, no more dilly dallying. No more deleted island. It's 3 a.m. I'm gonna finish this in 45 minutes. Full final exam. So full final exam review for chemistry 1. Okay, and so first topic is atomic. Oh, I spelled it wrong. First topic is atomic structure. Okay, and so when we talk about atomic structure, a few key things here we gotta know. Just talking about structure of atom. So there's 3 things. Oops, 3 things. We know that atoms are made up of protons, electrons, and neutrons. Right? And, you know, as the name suggests, neutrons are neutrally charged, okay? So they have a net neutral charge. Think of it like positive and minus. Positive and negative charge. And obviously for electrons, you know, you think about, what does electrons sound like? It sounds like electric, and you know, you tend to associate electric with like bad things, right? Like you don't want to get electrically shocked. So you think of it as a negative thing, and so this has a negative charge. Okay, and obviously a proton sounds positive, starts with a P, right? So this has a positive charge. That has a positive charge. And there's other things you have to know about these. Hold on, I need to burp. So please excuse me. Thank you. So, 2 of these are located in the nucleus, and 1 of these are located in the electron cloud. Now, I want you to guess, which one of these do you think is located in the electron cloud? Okay, well your answer is this one. Who would have thought? The electrons are located in the electron cloud. So these are located in the electron cloud, and the other 2, protons and neutrons, these are located in the nucleus. Okay. So that's the key difference between the 3 different I guess I can say 3 different particles of an atom. Okay, 2 of them are located in the nucleus, and the other one's located in the electronic cloud. Okay. Now, if we go forward a little bit more with this concept, what do you need to know about an atom? Okay. Well, an atom, or more so like an element, okay, has 3 things. There are 3 components. You have atomic number, you have the mass number, this is like the atomic makeup, and then you have ions. These are just key definitions that you probably should already know. And atomic number is simply your number of protons. Okay? Your mass number is your number of protons plus your neutrons. Okay? And an ion is just a charged particle. Okay, so it's just a charged particle. And there's 2 different types of ions. Okay, the first one is positively charged, and we call these cations. And our negatively charged ion is called an anion. And a really cool way to memorize these, or to not forget these, is cation sounds like cat, and cats have paws, right? Cats have... It's so bad. Cats have paws, okay? And cats have paws, so that means this is a positively charged ion. An ion sounds like onion, and we don't like onions, okay? Onions are no good. We don't like onions, so that's negatively charged. That's the pretty easy way to memorize these. Cation sounds like cat, and cats have paws, positively charged. Anion sounds like onion, they make you cry. It's not a good thing, so we call those negatively charged. And so the process of becoming an anion is, if you become negatively charged, do you lose or gain electrons? Well, if you become negatively charged, then you have to gain an electron. Okay, now some people think that if you become negatively charged, they think you lose an electron. And, you know, mathematically, you know, that kind of makes sense. Because when we're taught in math that we go backwards to get negative and we go forwards to go positive, right? So obviously if you're going this way, you want to count backwards, so you'd say you lose an electron. But an electron is negatively charged. So if you add electrons, you become more negative, right? So the process of becoming an anion means that you're gaining an electron, and the process of becoming a cation is you're losing electrons. That's the key difference between those two. And that's pretty much it for atomic structure. I'm not really going to go into different models. I think that's pretty useless. But that's the basic structure of an atom, what they're really made up of. You'll be asked questions, or we'll give you an element that will ask you, find the atomic number of the element, find the mass number of the element, what kind of ion is it, ask you all types of different questions, all pretty easy stuff, right? If they give you the mass number, right, so we know that our protons always equals our electrons, okay? So if you're ever asked to find the mass number and they only give you the number of protons, or they ask you to find the number of electrons given the mass number, you would just find the number of protons from the mass number, and then that would be equal to your number of electrons. So that's that. Oops, and now I need to save. Okay, well, our second topic is p-table trends. H2O, so you humpty dumpty billy boy, biggity bobbity, up. We still got 40 minutes left in class. I'm gonna need you to stay quiet. And thank you very much. So next, we're talking about periodic table trends. Okay, so if I have my periodic table, something like this. Oops. Something like this. Let's do this instead. Let me do this instead. And that's better. Yes. So it's something like this, right? And there's three things we want to talk about with periodic tables. One is our atomic radius. Second is our electronegativity. And our third is our ionization energy. These are honestly are all pretty similar, but they're kind of like inversely related, if that makes sense. The trend, at least. So the atomic radius. Okay, when we go down, we're saying down a group. Okay, and when we go across the row, that's kind of our trend for atomic radius. Okay, so when we go down a group, our AR goes up. Okay, and as we go to the right of a group, our AR goes down. Okay, so for here, you go to the right, our AR goes down, and when we go down, our AR goes up. Okay, that's the one for this. You know, this razor actually sucks. Interesting. That's okay. For electronegativity, it's actually the exact opposite of atomic radius, okay? So when we go right, our electronegativity increases, and as we go down, our electronegativity decreases as well. Okay, so these are literally the inverse of each other, the opposite. So our most electronegative ion is going to be our fluorine. Okay, so fluorine's like here somewhere, I don't know, this is fluorine. That is going to be your most electronegative ion. We don't call our noble gases part of this because they already have a full electron shell, and they don't really need to be electronegative, or they don't need to have ionization energy. Speaking of ionization energy, it has the exact same pattern as electronegativity. So as you go right, your ionization energy goes up, and as you go down, your ionization energy goes down. So you might be asking, like, what are the definition of these? Well, atomic radius means obviously how big is the atom, right? Like what is the radius of the atom? How big is it? That's all you're asking. Electronegativity is hold on. I just farted, I'm sorry. I apologize. Electronegativity is how well your atom can attract an electron. Okay, so it's how well your atom can attract an electron. And if you're thinking about it, if your atom is super small, right, from the atomic radius, if it's super small, it's gonna want to hold on to electrons, right? Because every atom has valence shells, right? And the smaller your atom, the more, I want to say, power it has to hold on to it. We call it electrostatic attraction. There's more electrostatic attraction from a small atom to the electrons in its shell. And that is what electronegativity is. How well it can hold on to an electron. Now, ionization energy, it has the same trend, but it means something different. Ionization energy means the ability to gain an electron. So how easy it is for an atom to gain an electron. And, well, this trend kind of just follows, you know, how many electrons do you have in your valence shell? Obviously, atoms with 7 valence electrons want to reach a full valence shell of 8. So every single one of our 7 atoms are going to be the highest in ionization energy. Right? And again, as you go up, you have the tendency to be able to gain an electron easier. The larger your radius is, kind of the harder it is for you to do that. So these two follow the exact same trend, while this one is inverse. Those are all the trends that you'll talk about in your tests. Okay. Next part, we're talking about the types of bonds. Okay. So, I feel like for chemistry, there's always just three things. There's ionic bonds, there's covalent bonds, and there's metallic bonds. So we have ionic, covalent, and metallic. And each one of these bonds have their own unique traits. Okay? So ionic bond is between a metal and a non-metal. Pretty important information that you have to know. A covalent bond is between a non-metal and a non-metal. And what do we think a metallic bond is? I mean, technically it is between metal to metal, but more specifically, it kind of just means we have a sea of electrons. What is burped? It smells like bulldog ramen. Interesting. But this makes sense, you know, from a holistic standpoint. Right, we have a metallic bond. If we have two solids bonding together, we know that solids have really compact, you know, electron formations. Right? So, it makes sense theologically. Well, let's talk about, you know, what these mean. When we have an ionic bond, our electrons are going to be transferred. Okay? So when we go on like a Lewis structure and we have something like this, NH4, right? All of these bonds connected H in the ends, these are all called covalent bonds because we're sharing them. Right? These bonds are being shared. In ionic bond, there's no sharing of electrons. Okay? So we don't really have any sharing of electrons in an ionic bond. So let's see for an example in H2O. Right? These H's and these O. Oops. The H's and the O's, right? Well, in H2O, because we have lone pairs kind of already on the outside of the O, these H bonds do not really connect with the oxygen in the center. Okay, so they don't really connect because there's lone pair repulsion happening, so it cannot really bond and have sharing of electrons. Right? And if you think about it logistically, H needs only one electron, but if you share, you have two. Right? So something isn't really making sense here. Right? So that's why think about it. H's to the O's don't really create the covalent bond. And next thing we'll talk about polarity. So we have two types of polarities. We have non-polar substances, we have polar substances. Non-polar just means that we have equal sharing of electrons, okay? So our electrons have equal sharing. And with polar stuff, we have electrons are uneven shared, or shared unevenly. Okay, so what that kind of looks like is, I'll make a new page. Say we have two molecules, okay, and they're bonded. Like this, right? They're bonded like this. This is nonpolar, right? Because they're shared equally. There's no pull to one side, right? But then let's think about a molecule. This side is negatively charged, and this side is positively charged. Partial positive charge, right? And let's say the electrons are pulled more towards this side, right? And we draw it like this, right? It's pulling it a little bit more to the right side, for instance, right? And like, let's just say that this was the example. It probably would pull towards this side, but let's just say whatever, it doesn't matter what direction, just an example, right? It's getting pulled towards a certain side because there's an uneven sharing of electrons, right? Due to charge differences, right? And so it's going to get pulled to a side. If there's any uneven sharing or electrons being pulled, you have a polar molecule. And that's that part. So our fourth part is basic chemical reactions. Okay. And for chemistry 1, we have very simple reactions. Nothing too serious. Nothing like organic chemistry, right? We don't have things like halogenation. Okay. To my knowledge, there's 5 basic types of reactions. We have synthesis. We have decomposition, single replacement, double replacement, and combustion. Right? And synthesis is pretty easy. Right? We're combining two things together. We have reactant A and B, and that creates AB. Decomposition, what do you think that is? That's the opposite, right? We're deconstructing something. So AB goes to A plus B. We see all this happening with acids and bases, so it's very important you know how to do this. With single replacement, we have things like AX plus B goes to BX plus A, and then with double replacement, you have something like AY plus BX goes to BX plus AY. Something along these lines, right? Very, very simple. We're just switching around the species with these molecules that are more likely to leave, and we're going to just slap them onto the other, usually the metal. The non-metal will usually leave, and the metal stays. Like an NaOH. OH leaves, and Na stays. And a combustion reaction is pretty simple. Fire is actually an example of a combustion reaction. Believe it or not, it does create water, just in a very minuscule amount. Right, so think about like what you need to put into a fire for a fire to happen. Right, so just think about it for a second. It's pretty simple, right? You need oxygen, and we're talking about specifically a hydrocarbon combustion. We need a hydrocarbon, right? So we have CXHY. We don't know how many carbons, how many hydrogens there are. We just know that it's a hydrocarbon, right? And what does a fire produce? CO2. That's why it's dangerous. Produces heat and water, right? And this water is very minuscule amounts, why you don't see it. But yes, the combustion reaction does create fire. The combustion reaction does create water, believe it or not, just in very minuscule amounts. And yeah, that's pretty much every single reaction type there is here. Once again, the hack for these reactions is that with single replacement and double replacement, the non-metal is usually going to be the better leaving group. Okay, so when you have two molecules. Again, like let's say you have NaOH plus something like FePb2. Okay, I mean this wouldn't really happen. This can't even happen. Let's say Fe. Let me say CaCl. Okay, well you would switch to NaCl plus CaOH. Okay, you're switching the nonmetals typically with the metal substituent to combine those two together. That's slow replacement. Single replacement is even easier, right? And the combustion reaction also very, very basic. So that's that for chemical reactions. Interesting, it's making me safe. Not sure why. There we go. Okay. And so the last thing I'm probably going to go over before I go to sleep, I'm tired, is the stoichiometry. This is kind of the big meat and potatoes of chemistry. So your stoichiometry. Basically just converting from moles to mass to moles. Right, so our basic kind of formula is moles to mass. 2 mass to moles. You might be thinking, what the heck does that mean? Okay, well you're going to be given the moles or something. Oh, you want to convert it to the mass. Okay, and how do you get the mass for that? Right, and then this mass into the mass of something else. Right, like say you have 6 grams of CO2. What is the mass of that? In terms of like in a reaction, you wanted the grams of H2O. Well, you would use this plus the molar coefficient given to you in the balanced chemical equation to give you the mass of H2O. Right, and this relies on you being able to solve mass to moles of the first species that you needed to compare it and to get the mass of the other species present in the reaction. Right, so it's important to know this kind of flow chart. You go from mass, moles to mass to moles. And a few things to know about this is our moles is equal to our molar mass, just the mass, over the molar mass. Yes. H2O, yes. Water. Very good. Really good H2O. Really good. I also love water here. I'll just show you a little water glass. Oops. Hey, it's not working. There you go. Just for you. A little water glass just for you. So yes, moles is mass divided by your molar mass, and then percent yield is another thing you kind of work with. Stoichiometry. This is going to be your actual yield over your theoretical yield. So what you could have made divided by 100. Right. So that's another kind of formula that we want to use, and that's gonna be pretty much it for this review. I gotta do like, once again, I'm not gonna go through actual questions. This is just a really brief overview of the Chemistry 1 curriculum for high school. When I do gas laws, sometime in the future, that one I will go more in depth in, because there are a lot of different gas laws that you can use and different applications for it. But yes, that is the the end of this review for chemistry 1. And I was tired, so this one might not be that good. Tune in next time, it's gonna be a lot better.